Euler angles. Euler angles represent the orientation using only three angles. These angles are originated from three successive rotations about the current or the mobile axis. There are several possible combinations of rotations, for example xyz, yxz, zxy, etc. There exist 12 in total. Note that there cannot be successive rotations about parallel axes. This means that, for example, I cannot have yx, because if I have yy, it will be just a single y, so it will be yx, it will be just two rotations, and not three as are needed for Euler angles. The most used are zyz, zxz, zyx, which are called Fick angles, yzx, which are called Helmholtz angles. We will only focus on zyz here. So let's consider this fixed frame. And now we're going to rotate an angle phi1 about the z-axis, and this will lead to this red frame. So the first is a rotation about z. Then we are going to rotate about the current y prime axis. We rotate an angle phi2. So the second rotation is about the current or new y prime axis. And the third rotation is about the current or new z double prime. So it's about this z double prime. We'll rotate again about this z double prime. And we get the final frame, which is this green one. The equivalent rotation matrix would be as follows. First we are rotated about z. Then we are rotated about the current y, so we post multiply. And then about the current z, so we again post multiply. So it's this z phi1 post multiply y phi2 and post multiply z phi3. If we operate, we get this big matrix, which takes us from Euler angles to a rotation matrix. If we want the opposite problem to get zyz angle Euler angles from a rotation matrix, we have to compare this. That the problem is given this rotation matrix, we want to find the zyz Euler angles. Using the previous matrix, we can see which are the terms that we can use. So in this case, we are not interested in these terms. We can only use these four terms. Why? Because the rotation matrix is redundant. So these 5 terms provide us enough information. If we compare and solve, we can get this expression. Here we can note that if phi2 goes from 0 to pi, then it's a positive sign. If we use the negative sign here, phi2 would go from minus pi to 0. Then we have the elements for phi1, and in this case this has to be different from 0, this sign phi2, and also phi3. Now look that there are always two different solutions which correspond to taking this plus or minus sign here. And also this sign has to be always different from 0. So when this is equal to 0, we have a problem, and that problem is called a singularity. So there's singularity when phi2 equals 0, pi to pi, etc. If we consider 0, then the sign is 0 and the cosine is 1. If we replace it in the first matrix, the big matrix, where we have all the elements in terms of phi1, phi2, and phi3, we will end up with this expression. So from here, we can only recover phi1 plus phi3. We have completely lost the information about phi2. If phi2 equals pi, then this sign is 0 and the cosine is minus 1. We again plug in the big matrix and we get this expression. So in this case, we can only recover phi3 minus phi1. Let's see an example. We want to find the rotation matrix equivalent to this zyz Euler angles. So you can just apply the definition of this, the rotation about z of 30, about x of 50, about z of 90. You get the matrices for each of these elements, you multiply and you get this result, which is the equivalent rotation matrix. Now we want to find the equivalent rotation matrix to the zyz Euler angles shown here. If you do the same procedure, at the end you will end up with exactly the same matrix. Why is this? Because as you remember, there are two pairs of Euler angles, always for the same representation. Given the previous matrix, we want to find the possible zyz Euler angles. So if we only have this matrix, we should be able to get this Euler angle and also this set of Euler angles.